In today's video, here is a nice and choose problem that was just previewed. Here is the following information. Find all ABC as integers, satisfy this following equation. So we get 2 to the a plus is multiplied by 3 to the b plus number 1 equals c squared. Okay. Indeed, solving this equation in integers is better to solve it in non-negative integers or positive integers, because it's very important to include 0 as a solution as well as negative solution, because 0 here is going to give us some solutions, and also the negative solutions is going to be included here due to the perfect square, because you may have a positive or negative solution. Okay, now let's go through the solution to see what's giving us. Okay, first of all, I'm going to move over this number 1 to the other side and make a product. So we'll have the following. So I get 2 to the a is multiplied by 3 to the b, which equals c minus number 1 factor c plus number 1. Okay, because I have a factorization prime here, I'm going to work on 1 prime. So I'm going to put a equals 0 and leave the other one is free. On the other side, I'm going to leave 1 is free, the other one 0. So let's fix if a equals 0. So I will have here 3 to the b equals c minus number 1 factor c plus number 1. It's clearly I have a power of 3 here, so which means each term of this product must be a power of 3 as well. So I get here, I get c minus number 1 equals 3 to the x. The other one I get c plus number 1 equals 3 to the y. So it's more simple. I'm going to solve this equation by taking this equation and minus this equation. I will have number 2 here, which equals 3 to the x factor 3 to the y minus x minus number 1. Okay, it's clearly y must be strictly superior than x. So it's more simple here. This one is an even, this one is an odd. So we don't have odd here except number 1, which means x must be 0. Okay, so this one immediately x equals 0, which means c equals 1 after you taking this minus number to the other side, so which means c equals 2. So we don't have to solve this one because we found out c equals 2. So it's clearly I'm going to find b in this case, because I know a. So I will have the first solution. I get a equals 0 and I get c here equals 2. I'm going to find b. I have here c, which is 2 square, which is 4. 4 minus 1, which is 3. I get here 1, so which means b equals 1. So b equals 1 here. So I have first solution. So let's find out the other solution. This time I'm going to take b equals 0. And I will have 2 to the a. Almost I will have the same job here. I got 2 to the a is multiplied by equals c minus number 1 factor c plus number 1. So it's clearly here I will have the same thing. I get c minus number 1 equals 2 to the I. The other one I get c plus number 1 equals 2 to the j, where is j strictly superior than I. Doing the same thing, taking this equation minus this equation, so I get number 2, I get c cancelled out. I will have 2 to the I factor 2 to the j minus number I minus number 1. Okay, it's clearly this one is an odd, so which means this one equals 1. I equals 1 because we get number 2 here as an even integer. So I get I equals 1. If I equals 1, which means here I get 2 here. So simply I get c equals 3 because I'm taking minus number 1 to the other side. I get 2 plus 1, which is 3. So I get c equals 3. I'm going to find other integers. Don't forget I have another solution here, because if you replace c with minus 2, I will have another solution. Let's take another solution for this one. I get a equals 0 b equals 1, c equals minus 2. Here is a second solution. I'm going to complete this solution. So I will have a, I'm going to find out a, I have b equals 0, I already have c equals 3. Finding a, I'm going to replace these values into the original equation. I will find a. So I get here c squared, which is 3, which is 9. 9 minus number 1, which is 8. So this one, it was 1. So get 2 to the a equals 8, which means 8 equals 2 to the 3, which means a equals 3. A equals 3 here. So by taking the negative solution, I get also another solution. So I get a equals 3, b equals 0, and c equals minus 3. So let's find another solution. If you take a look carefully here, I get number 4 is multiplied by 6, which equals 2 square is multiplied by 6 equals 2 is multiplied by 3. I'm going to join this one to the other one. I get 2 to the 3 is multiplied by 3. If you take a look carefully here, if you take a look at this product, so this one differ by number 2, okay? Because between this number and this one, you will have a number 2 as a difference, okay? So also here I get 4 is multiplied by 6, which is this one also is differ by 2. I will have number one of these is divisible by number 3, okay? So which means I get here c minus number 1 factor c plus number 1, which equals c squared minus number 1. So I get number 1 here. C minus number 1 is going to be replaced with number 4. C plus number 1 is going to replace with number 6. So I'm going to create another solution here. So I will have another solution here. I get a equals 3. I get b equals 1. I get c here, because I get 4 is multiplied by 6, which is 24. I'm going to take this minus number 1 to the other side. I get 24 plus number 1, which is 25. 25 is the same as 5 squared, which means c equals 5. Okay, let's check another type of the solution. So I get 16 is multiplied by 18, which equals 2 to the 4 is multiplied by 2 is multiplied by 3 squared. I'm going to add this one in the exponent. I get 2 to the 5th is multiplied by 3 squared. As I said before, this 16 is multiplied by 8 is the same as 288. This 288 is the same as 289 minus number 1 is the same as 17 squared minus number 1. Okay, so we get c equals 17. So now I'm going to determine the values a, b, and c. So we get this one a, this one is b, this one is c. So it's more simple. I get another solution. I get a equals 5, and I get b equals 2, and c equals 17. Okay, but be careful here. I'm going to create another solution here. So I get here a equals 3, b equals 1, c equals minus 5. Also here I get a equals 5, b equals 2, c equals minus 17. Okay, so previously we have determined the number of the solution was 8, but we still miss one solution. Okay, so the solution that I have missed, when we take a look up here, we have 6 is multiplied by 8, which equals 2 to the 3 is multiplied by 2 is multiplied by 3. So I'm going to put these 2 to the exponent. So I get 2 to the 4 is multiplied by 3 to the 1, which equals 6 is multiplied by 8, which is 48. 48 is the same as 49 minus number 1. 49 is the same as 7 squared minus number 1, which equals c squared minus number 1, which equals c minus 1 factor c plus number 1. Because this one, because c minus number 1 and c plus number 1 differ by number 2. Okay, So it's clearly we are going to determine C now, because C is, now it's clearly we have a solution of A equals 4 and B equals 1 with C equals 7. Since we are considering the negative solution for C, so I will have a second solution. I get A equals 4, B equals 1, C equals minus 7. A and B are always positive, okay? So now we have the number of the solution are 10, okay? Now let's get rid of this one and move on to the general proof. If you take a look, the last solution, it was C equals 17. What about if C is greater than 17? So we are going to prove we have no solutions beyond that point, okay? Now let's get rid of this one and move on to the next case. So I'm going to tick, so let's do that by the way of contradiction. Suppose C equals 23 plus 2n for all n is super equal to 1. You might say, why I'm going to write C on this form? Because C is odd. If you go back to the original equation, you will find C is odd. So this means the odd is going to be written on this form. But we are skipping some odd integers. We are skipping 17 plus 2n or 19 plus 2n. Because I have worked on that cases, and none of those cases it gave me a contradiction. This is the convenient value which is going to help us to build a nice contradiction, okay? Now let's take this value of C and then sort it back into the original equation to see what's the next expression. So we'll have 2 to the A is multiplied by 3 to the B, which equals C square is going to be replaced with this one. So I get 2n plus 23, all is raised to the number 2 minus number 1. I'm going to distribute this one out. I get here 4n square. I get here 4 is multiplied by this one is going to give us 92 n plus 23 square minus number 1. So this one is going to give us 4n square plus 92 is multiplied by n 23 1, which is 440. So I'm going to divide both sides of the equation by number 4. So I will have here 2 to the A minus 2, but be careful here. For all A must be super equal to 4. For A is super equal to 2, okay? To keep this one as an integer. This one is multiplied by 3 to the B, which equals n square plus 92 divided by 4 is going to give us 23 n plus this one divided by 4 is going to give us 110. Okay, now I'm going to use a nice trick to make this one on the form of the quinary square. So I'm going to write this one as n plus 7 quinary square. If I'm going to distribute this one, it's going to give us n square plus 14n to get to the 23, which means we are going to add 9n plus 9n. 110 is the same as 99 plus 33. Okay, also 33 is the same as 27 plus 6. Okay, 9, but keep in mind B must be super equal to 2 here. Okay, so since B is super equal to 2 here, so I will have number 9 here at least. So now we are allowed to divide both sides of the equation by 9. In the other word, I'm going to reduce the equation to the mod 9. Okay, so I get 0 here, I get 0 here, I get 0 here, I get 0 here. So I will get this one square plus number 6 are the reminders of this equation. So I get here n plus 7 quinary square. This one is already 0. This one is 0, the other one is 0. So I get here 6 as a reminders is a congruent to 0 mod 9. Okay. Now I'm going to move over this number 6 to the other side. And also I'm going to put this one as a x. Okay. So I get here x squared is a congruent to minus 6. I'm going to add number 9 on both sides. Plus 9 is going to give us 3 mod 9. Okay. Now since I get to this case, this is very important. This one I'm going to take it as a original statement. I'm going to prove the perfect integer and take some cases by using the chart in order to make a nice comparison between two perfect squares to see what's the possible reminders when we divide this one by 9. Okay, so let's do this one. So let's take k following the values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So this one is going to be reduced to mod 9. Okay, now I'm going to take k square. I get 0 here, I get 1, I get 4, I get 0 here because 9 is divisible by 9. I get 4 square, which is 16, 16, 7 more than 7, so I get a remainder 7 here. I get 25, I get 7 more than 18, 7, 6 square, 36, 36 divisible by 9, I get 0 here. 7, 49, 49, I get 4 more than 45, so 4, 64, 8 square, 64, 64, I get 1 more as a reminder. 9 is clearly 0, 10 is 99 plus number 1, 99 is divided by 9, so I get a remainder number 1 here. It seems we have only 0, 1, 4, and 7 are the possible reminders. So I get here. So find here the perfect square, x square, is always congruent to 0, 1, or 4, or 7 mod 9. Okay. Since we have an absence of number 3 here as a reminder, which means it's a contradiction. Which means we have no solutions when we have c is strictly superior than 23. Okay. But below the point 17, c equals 17, we have couple solutions, and checking c equals 19 and 23 also are not the solutions, and adding to this general case, which means we have no solutions for this equation above this point. So yeah, I have done this problem. Thank you for watching. We will see you next video. Bye.